Hello, so continuing on this week's biweekly challenge or biweekly contest, the third problem is shortest subarray with or at least k, 2. So a little bit of a long title here, but we have an array of positive numbers and we have an integer k. And we have this concept of a special array, where an array is special if the bitwise OR of all the element is at least k. So basically bigger or equal to k. And then what we want to do is find the length of the shortest special non-empty subarray. So the shortest subarray non-empty that has this condition, where all the bitwise OR of all the elements is bigger or equal to k. And if we are not able to find any such array, we can return -1. So that's the idea. Now, the constraints are too big, 10 to the power of 5. So that completely eliminates going through every single subarray by just doing 2 loops, because then that would be too expensive. So we can't do that. We need to find another solution. So let's see how we can tackle it. Okay, so how can we handle this? Well, the first thing to analyze here is the problem asks us to do the subarray, right? We are tackling subarrays, and what we want is the cumulative OR of that subarray needs to be bigger or equal to k for us to be able to call this subarray special. Okay? And so how can we do this? Well, the first thing is subarray and accumulating something and then doing the condition. If you've done the past couple of days daily challenge, you will realize that most of the time that can be solved with 2 pointers or sliding window technique, right? And as we said in previous videos about these, in the past couple of daily challenges, you need to define 2 things: how you do expand, how you would collapse, and if that will actually get you the answer, right? So we need to think about that for a second. But before that, we need OR to sort of have this to sort of have some pattern where basically we can, if it increases, we know that it will keep increasing if we add more numbers, right? And so that we can decide to expand or collapse. And if it decreases, we need to know that this value will decrease, right? Okay, and so is that true? So for OR, one interesting characteristic is, what is OR even? OR is, if you OR 1 with 1, you get 1. 1 with 0, you get 1. 0 with 1, you get 1. 0 with 0, you get 0. Right? So what is the thing here? If you have 1 on whatever side, you will always have 1 on the other side, right? So even if you have, let's say, a number like this with binary and maybe with some 0 in the middle, let's say something like this, right? And then you have something with zeros, right? Let's just assume all zeros except the last one. Then you would have still the same bit places that had binary 1, they will have 1 here. So this basically tells you that if you OR more numbers, even if those numbers don't have 1 on the expected place, on the same places as the previous number will not be reduced, right? Because whenever there is 1, there will remain a 1 in that position. So the number here, if you add more numbers, so OR, adding numbers, or ORing with other numbers, let's call it ORing. So OR with new numbers will only either stay the same or increase, right? It will never decrease it. That's really important for this, for us to be able to make calls here. And similarly, if you remove a number, let's say you had a number that was an OR of A, B, C, D, and you remove A, the number will either stay the same or be lower, because of the same reason. If there was a 0, then the number will, if there was a 0, then one number will not be affected. If there was a 1 and we remove that 1, the number will get reduced, right? Because we removed a 1. And so basically removing a number from OR, either it will stay same or it will reduce. Okay? So with these two characteristics, how can we apply them to our sliding window technique? Okay, let's go back here. So we need to find our expand condition and our collapse condition, right? Now, when should we expand and when should we collapse? Well, we know definitely, like, the problem says we want the shortest special subarray, right? So if we reach an OR where the value is bigger or equal to k, there is no need to expand further, because we already found a special subarray. So our best is already equal to this special subarray value. Let's call it x. If we expand more, we'll increase x by 1. The length would be x plus 1, right? But x plus 1, we already have a better answer, so there is no use to expand. So we definitely know that if it's bigger or equal to k, we don't need to expand. So that leaves us with, if it's not, expand, right? So if it's smaller than k, we expand. That's our condition. If the OR smaller than k, but by the way, the OR here is for our current window, so that would be from I to j for our sliding window here. However, we should collapse, because when we have an OR that is bigger or equal to k, we want to reduce it, basically because maybe, let's say we are I here and j here, and this here is bigger, the OR is bigger or equal to k. Why do we collapse? Because maybe this subarray here has a better answer with, let's say, j minus 1, j, and the j plus 1. Maybe that one has an OR bigger or equal to k. We don't know, right? And if it does, this one has a smaller size. Let's say this one size is 4, and maybe this one size is 5. This one has a smaller size, so this one may be a better answer, right? So if it's bigger or equal to k, we need to collapse so that we have a chance to reduce the number and maybe pick up another number, and get a smaller OR, or even maybe even this was the OR of only like a smaller subset is even bigger or equal to k, right? So that's the key idea here, is we collapse if the OR is bigger or equal to k of the window, and we expand in the else case, okay? Now, so now that we came up with that, we can just apply our template of sliding window where we keep moving j, and then we do a while loop where as long as this is bigger or equal to k, we move the left pointer, we collapse, which basically means we move the left pointer by 1. But now our problem is, how do we keep track of this, and how do we, when we do I plus 1 here, we need to remove the element at position AI, we need to remove it from the window, from the OR of current window, right? Because this I is no longer part of our window. And similarly here, when we expand and add an I, we need to add a j to OR of window, right? Okay. And so how do we do this? Well, for the first one, you may say it's easy. We can just keep track of the current OR, right? We can just keep track of the current OR and just OR it with a j. Okay, but this one is tricky because with OR, it's tricky to reverse to have the reverse operation, to have like a definitive, non-ambiguous reverse operation where you remove an element that you have added before. Like if you have A, B, C, and you want to remove A, for example, this, let's say the OR is these 3 elements, and you want to remove the A from the OR, there is no definitive operation that will remove it, okay? And so how do we do that in that case? Well, with binary, there are 2 ways to represent it. You can represent it with a number, or you can just represent it with a frequency table, right here, of size 32, which is the number of bits. Now, if we use a frequency table, we can just keep track for each bit how many numbers in our current OR have that set to 1. Okay, so for each bit in, so what we can do is for each bit in the range up to 32, we can just set if we are adding a number, we can increment, say that this bit now occurs +1 times because of the new number, right? But we do this only if the bit is set in the new number, right? If the bit is not set, it's 0, we just leave the frequency number as it is, right? But if the bit is set on AG, we can see that formula later, has bit set, then we increment. And this would be basically adding this to the OR. Now, our OR representation is going to be just this frequency table. Now, in the same vein, to remove it, we can just subtract by -1. So it makes it really easy. So to remove, we can just say, do the same loop, but in this case, we do frequency bit -1 because we are removing this number from the OR. So when it reaches 0, we will know, right? But now you may say, okay, how do we find then that the cumulative OR is bigger or equal to k? The frequency table, right? And so from the frequency table, we can get the actual value of the OR. We'll see that in the detailed implementation, but that's the essential idea here, is we will use a frequency table to represent our window. And then with the expand and collapse, we'll use the property that with OR, if you add more numbers, the number either stays the same or increases. With removing, it either stays the same or decreases. And from there, we were able to come up with our expand and collapse condition for our sliding window technique. That's the general idea. Now let's code it up. Okay, so let's code this up. So what we need first is we need our bit frequency, right? That keeps track of the frequency of each bit. And we just need it for the number of binary numbers that we'd have, which is 32. And so this would be just for the range of 32. And then what we need is to just get together our sliding window structure. So J will keep it moving. And for this, and we will expand for each J. And for the collapse condition, so we'll do while collapse condition, basically, will collapse. Okay? And so what is our collapse condition? We said it's while the current OR, which we need to define, by the way, we need to get the current OR out of the bits frequency. So let's just have a function, let's call it get the OR from the bits frequency. Okay, so that will return us the bit frequency. We'll implement it in a second, but we'll need to get the current OR value from the current bit frequency. So I'll just call this function. And while this is bigger or equal to k, we said, that means we already found a best answer because it would be the smallest one that is bigger or equal to k. So we'll need to reduce our window. And of course, we'll need to make sure our window is still valid by making sure I is still smaller or equal to j. And then we need to also just initialize I here. And then we collapse. How do we collapse? Well, we definitely need to increment I so that we move the pointer to the left. But we need to update our bit frequency. So let's just call the function remove from bit frequency. And what do we need to remove? We need to remove the element at position I because we are moving the pointer to the left. So AI, okay? And that's pretty much it for this one. But since we keep doing this while current OR is bigger or equal to k, we need to update the current OR value with the removed after we remove it from the bit frequency. And so let's just call this again, the function again. And now we need to call expand. So what should we do for the expands? Well, we want to add a g to the bit frequency. So same way that we have a remove from bit frequency function, we need an add from bit frequency. So this will need to be passed the bit frequency and the element. Okay, so something like this. And we said we need the same thing for adding to the bit frequency, right? So that would be something that, sorry, this is all mouthful, but it should be pretty simple to implement. So with the expand, we want to expand, we want to add the value at position j to the bit frequency. So this would be add, okay? And that's pretty much it for the core thing. Now we just need to implement these helper functions here. But at the end, what should we return? Well, that's the key idea. Now we are looking for the shortest. So we need to keep track of some value that will get us the shortest one. So I'll just have this infinity and just a big number, right? Let's call it float inf. And now with this best, each time we want to update it here, right? And so we say when we collapse, because when we collapse, and it's still bigger or equal to k, so it still has the condition we are looking for. So it's still special array. And so for that one, we want to get the minimum possible. And the minimum is j minus I plus 1. So this is the size of the window of the subarray. And each time we increment I, we reduce the window size. So we want to check if that's the minimum we have so far. And then at the end, we just want to return best. But we want to make sure, like, let's say, for example, we never were able to find an OR value that is bigger or equal to k. In that case, best would still be equal to this big value. And so, but the problem asks us to return -1 if we are not able to find a special array, a special subarray. And so we need to check if best only is different than the infinite value, which means it was changed, we return it. But otherwise, if it wasn't changed, that means we weren't able to find anything, so we return -1. Okay? And that's the general structure, which this should be overall of time. Now let's implement this. So first add 2 bits. Well, we just need to go through every bit in the range 32. Check if it's present in this value we want to add. And so if A, this is basically just checks if the bit is set. You just need to make sure you go back and understand it and make sure you really know how to check if a bit is set. That's really important with Leetcode and algo problems. But we check if the bit is set, then we want to increment the bit frequency by 1, right? Because it's was set. And all of this is we want to know when we reach 0, because when we reach 0, the value will reduce by that position moving from 1 to 0. Now, for removing, it's very similar, except we want to subtract, right? Because we are removing the element. And then, how do we get the OR value? So let's call it OR. Let's call it maybe bit OR or something like that. Now, what do we do? Well, same thing. We need to go through every bit. And if it's set, which means basically if the frequency is bigger than 1, that means it's set, like, right? Because when you OR 1 and 1, you just get 1, 1, right? So if this is set, which means this is bigger than 0, then we want to set the bit OR with a value that makes that the position at bit set. And that's just 1 bit. So basically, let's say the bit position is 2. This will basically OR with 0, 0, 1, something like that, right? Okay, and then we want to return this. Okay, so this is all should be pretty simple, and it's all constant time because it's all 32 iterations, and so it doesn't add anything to this, so it stays at O1 time. And then for extra space, we are only using this bit frequency, which is constant space because it's 32 elements. So let's run this. We need to define n, which is going to be just the length of our array. Let's call our array A, because we are using it as A here. Can run this. Gets accepted. We can submit. And that gets accepted. Okay, so I hope that was useful. Sliding window technique, the key thing is to remember the properties of OR and to realize that for the window, keeping track of the window, we need to actually use a bit frequency table and not just a value for OR. Okay, yeah, and that's pretty much it. Thanks for watching and see you on the next one. Bye.